All right, so this is the extended lecture. So this is going to have a little bit of mathematics. All right, so this is the mathematical portion of the lecture that we got started on the electromagnetic wave. Observation.
30 years ago, space was considered a vacuum, except for a curious clue, the tail of a comet. Regardless of the direction it traveled, its tail always pointed away from the sun.
All right, so this is the observation that Newton was making in 1600s. He noticed that the tail of a comet points away from the sun. So his question is why? Obviously, gravity is acting on the comet as well as the tail. And whatever the tail is made up of particles, so that's fairly obvious to Newton. Today we know that the tail is composed of ice as well as the dust particles. So the question is, what's coming out of the sun, which is pushing away the tail? So there's something being emitted by the sun, which is colliding with the particles making up the tail and pushing them away from the sun. So that's what he's pondering about. All right, so this is roughly about 400 years ago, and this is the question that he has, and his conclusion is light must be composed of particles. That's what he's thinking. So why is he thinking that the light is composed of particles as opposed to waves? All right, Newton on the left, he's thinking that the light must be composed of particles. And the guy on the right is Christian Huygens. All right, Huygens proposed that the light is composed of waves. The reason why Huygens thought that the light was composed of waves was because he had been conducting experiments using light. He noticed that the light would undergo an interference phenomenon. Only waves can do interference. So as we all know, the wave is a traveling disturbance that carries energy as it's going from one place to the next place. And the waves can interfere either constructively, and when they do, amplitude is going to become maximized, or destructively, and when they do, amplitude is going to get canceled out. He knew that by using light sources, you can actually make light brighter. That means constructive interference. Or you can cancel out light in such a way that absence of light is one of the things that happen, or the light is going to become dimmer. So you can make the light brighter through constructive interference, or you can make it dimmer through destructive interference. So to Huygens, this meant that the light must be a wave. So what is Newton's argument if that's the case? Newton is thinking, wait a minute, with waves you can transfer energy, so that's fairly obvious, but you cannot transfer momentum. The fact that the tail of a comet points away from the sun, that means that these particles are being pushed away from the sun. The only way you can push these particles away from the sun is through particles colliding with other particles. So that meant to Newton that the sun must be ejecting particles in the form of light. That to him meant that the light must have a particle nature. As far as Newton was concerned, despite the fact that they didn't have the concept of energy back then, but just think of it this way. If wave is a disturbance that carries energy, when a wave like the electromagnetic wave, which happens to be a transverse wave, what would happen to the particles? When the wave is coming through, the particles are just going to vibrate up and down. They're not going to get pushed in the direction of the motion of the wave. So as far as Newton is concerned, waves cannot transfer momentum. Only the particles do. And on that basis, he thought that the light would be a particle, not a wave. Do you guys think that Newton had the right idea? In a sense that the waves cannot transfer momentum, only energy? Is it possible? Is it also possible that the waves can also transfer momentum? So that's something that we will get to investigate. So electromagnetic fields. So let's talk about the Maxwell's equations. Everything can be traced back to this guy, Oersted, 1819. So he's doing his simple physics experiment. While he was lecturing, he runs a current through a wire, and there's a magnet there's a compass nearby, so he sees a deflection in the compass. And he immediately concludes that what causes magnetism is the current inside the wire. So the electricity or the currents generate magnetism. If the current is going in the opposite direction, notice that the magnetic field is going to wrap itself around the current wire, and the direction of the magnetic field can be determined by using the right-hand rule number 2. So this was something we discussed exclusively. About 10 years later, in 1830, Maxwell discovers that by using magnets, you can generate electricity or electrical current. In his mind, what's happening is, and then he takes these two concepts together. Obviously, the current generates magnetism, and the magnetism generates currents, and he combines these two concepts into the concept of electromagnetic waves. Electric field component is going to be generated by using an AC generator. So you will get a wire, and then you will run a current through it up and down. So what drives the current is the electric field lines, and these electric field lines driving the charges up and down is going to radiate away from the wire at the light speed. So this gives you the electric field component of the electromagnetic field. So where do we get the magnetic field component? We will get the magnetic field component from the Oersted's discovery. When the current is going in the upward direction, notice that the magnetic field wraps itself around in the counterclockwise direction. If you reverse the direction of the current, the magnetic field is going to traverse, or it's going to curl around the current wire in the opposite direction. So what's driving the current in the opposite direction is the electric field, so which means that the magnetic field wraps itself around the electric field one way. And then when you reverse the direction of the current, the magnetic field is going to wrap itself around in the opposite direction. So what that means is any variation of the strength of the electric field is going to create the magnetic field component. Any variation within the magnetic field is going to create the electric field component. Thus, it turns into an electromagnetic field or wave. So electromagnetic waves, as you all know, will travel at the light speed. And Faraday was the guy who came up with the concept, and Maxwell is the guy who was able to formulate it. All right, these 4 equations that you're looking at are known as the Maxwell's equations, so we will go through each and every one of them, despite the fact that the Maxwell's only contribution is the very last one, far to the left. All right, so the very last one that you're looking at is the Ampere's law, and right after that, you got the Maxwell's contribution to it. So Maxwell's contribution, simply stated, if you just vary the strength of the electric field in a given region, it's going to cause a circulating magnetic field. That's it. All right, so before we go through the derivation, before we go through the Maxwell's equations, let me just briefly go over each and every single equation. The first one is the Gauss's law. Simply stated, charge within the Gaussian region is going to be responsible for the electric field intercepted by the Gaussian surface. The second one is, once again, the Gauss's law. So the first one, the net charge within the Gaussian surface, is going to be responsible for the electric field intercepted by the area of that surface. And because of the fact that we don't have magnetic monopoles, which means that we don't have a single magnetic pole, the net pole within the Gaussian region is going to be 0. All right, so you will have equal amount of north and south poles. That's what it means within the Gaussian region. So which means that the net magnetic field within that region, the Gaussian region, is going to be 0. The third equation that we are looking at, which is this one, this is the Faraday's law. Any variation of the magnetic flux, any time variation of the magnetic flux, is going to cause a circulating electric field within that region. And the last one is the Ampere's law. So the current within the wire, according to this, is going to cause a circulating magnetic field. And then Maxwell also notices that if you vary the strength of the electric field within that region, it's also going to cause a circulating magnetic field. That's it. So out of that, when we solve the equation, we will notice that the electromagnetic fields travel at the light speed. So, Maxwell's equations. The first one is straightforward. Net charge is what creates the electric field within the Gaussian surface. So the amount of electric field intercepted by the area of the Gaussian depends on the net charge on the inside. The next one is, once again, the net magnetic dipole is what generates the total magnetic field intercepted by the area. In this case, it's going to be 0 because magnets are dipoles. The third one is based upon what Oersted discovered. Current causes a circulating magnetic field. I forgot to do the integral sign there. And the last one, simply stated, is if you vary the strength of the magnetic field within a certain region, that has an area, it's going to change the magnetic flux is going to generate a circulating electric field. That's it. So that's what Faraday came up with. So the question is this. This is what Maxwell was trying to prove. If you vary the strength of the electric field within a certain region, could it cause a circulating magnetic field within that region? So that was the question that he was trying to answer. That's the theory that Faraday came up with. So he came up with an ingenious way of solving this problem. So he looked at a capacitor within which the electric field strength is constant. And then he decided to charge it up by hooking it up to a battery. So it's going to create a current. So the current is going to simply charge it up. So the current is going in, charging up the capacitor. When you charge up the capacitor, the strength of the electric field is going to increase within the capacitor. So you have a current-like term inside the capacitor. Right? It's not quite a current because there's no current within the gap of a capacitor. So the strength of the electric field is changing. There's a current-like term that we're looking at. So isolate that current-like term in that formula. And call it the displacement current because something acts like a displaced current within, once again, within the space or gap of a capacitor. All right, and so once that term is isolated, you can take that and you can take it back to the equation that Ampere came up with for the Oersted's discovery. And this time let's put in the integral sign. So make that the displacement current, and when you make it the displacement current, you will notice that if you vary the strength of the electric field within that region, it is going to cause a circulating magnetic